This video looks at applications of circular motion. Now consider a particle tied to a string to a fixed point, O, which you can see in the picture. If the particle moves in a horizontal circle so that the string describes a cone, then the string and the particle form what is known as a conical pendulum. And I've drawn this diagram to try and help understand all of that. So things to take note of. This is your fixed point, your O. This is your length of your string. You have a force upwards, which is your tension. Okay, I've put it as TE so it doesn't get mixed up with period. But there you go. And then your particle is this point P. Okay, so on that particle you have a downwards force, which is your weight, equal to mg. Okay, and the angle the string makes with the horizontal is theta, which is here. And if we just look at the forces, look at this diagram here, you can see those forces resolved, or the tension resolved into its horizontal and vertical components. Okay. And I just noticed I missed a little E for tension there. I have put a bunch of rules to the right hand side. Maybe keep those in mind when you're doing the examples and questions. In the first few examples, I actually derived the rules rather than remembering them. So it's up to you what you do. So let's move on to some examples. First one, a small body attached to a string to a fixed point describes a horizontal circle at a uniform angular speed of 1 revolution per second. Show that the distance below the fixed point does not depend on the length of the string. Okay, so if you think of what's going on here, okay, this is our theta, point O, this is at right angles. This is our small body. The weight of it going down is mg. We have tension in the spring. I'm just going to use T when I do these questions. Our length of our string is L. So if we're thinking about resolving, this is going to be L sine theta, our horizontal component using trig. This is going to be L cos theta, our vertical component, again using trig. And also note that this is also theta, parallel lines, alternate angles. So that's my L cos theta as well, just so you can see those forces acting against each other. And our angular velocity W. Okay, or omega. Okay, so we're going to resolve our tension horizontally and vertically, which we've done on the diagram. So vertical is equal to L cos theta, horizontal is equal to L sine theta. So that's resolving tension. Okay, so T sine theta is going to equal our mass times by, I'll put in the point P, the distance Pn, which would be the radius if you're thinking about the circle, times by omega squared. So that's going to be m times L sine theta times omega squared. So our tension, if we divide both sides by sine theta, is equal to ml omega squared. Or you could remember the formula. Okay, T cos theta is going to equal our mg. So mlw squared, which is our tension we just found, times cos theta has to equal mg. So I should put, that's equation 1 sub in 1. So that's how we get to that. So L cos theta is going to be mg over m omega squared, which is g over omega squared. And that is what our ON is equal to. Okay, our vertical component. But L cos theta equals ON. Okay, as I just said, which is the vertical distance of our body P below O. So therefore, the distance of P below the fixed point doesn't depend, or is independent of the length of the string. Okay, next find the tension in the string if the mass of the body is 1.5 kilograms and the length of the string is 40 centimeters. So P moves with angular velocity of 1 rev per second, which is given in the question. So omega equals 2 pi, because that's our circumference. Our m equals 1.5 kilograms. Our L equals 40 centimeters, which is 0.4 meters. So our T is equal to ml omega squared. So that's going to be 1.5 times by 0.4 times by 2 pi all squared, which is 0.6 times 4 pi squared, which is approximately 23.7 newtons. So therefore, tension in string is approximately 23.7 newtons. Okay, next example, 4 kilogram mass is attached to a string 60 centimeters long. Calculate the maximum number of revolutions per second that the pendulum will be able to complete if, for safety reasons, the greatest tension allowable is 400 newtons. So again, I mean, you can just use the formulas if you want, or you can draw a diagram and resolve, which is what I'm going to do here. Our horizontal component always will be our radius, so r is going to be equal to 0.6 sine of theta. Okay, so that's that. So resolving tension. At P, T sine theta is going to equal mr omega squared. M is equal to 4 kilograms. My L is 60 centimeters, which is 0.6 meters, which means my radius is 0.6 sine theta, which I already put on the diagram. So T sine theta is going to equal 4 times 0.6 sine theta times 2 pi n all squared. N is the number of revolutions per second. Okay, so that meant that omega equaled 2 pi n. So I've now got, that's 4 times 0.6 sine theta times 4 pi squared n squared. So that's going to be 9.6 sine pi squared n squared. And I forgot the theta. That's better. And that's t sine theta. So if we divide both sides by sine theta, we end up with t equals 9.6 pi squared n squared. But our maximum possible tension is 400 newtons. So T has to be less than or equal to 400 newtons. Now the textbook says less than 400 newtons, but it does say that it can have a tension of 400 newtons. So I think it should be less than or equal to. The other way of writing that is that 400 newtons has to be greater than or equal to T. So that means that 400 has to be greater than or equal to 9.6 pi squared n squared. It's actually better having it the other way. 9.6 pi squared n squared is less than or equal to 400. Start rearranging, get n squared on, get n on its own. N squared is less than or equal to 400 over 9.6 pi squared. So n has to be less than or equal to square root of that. Plug it into your calculator and you get 2.05. Oh, and I should have said n can't be negative, which is why we only took the positive value. So therefore, and it actually is 2.05 something. So the greatest number of revolutions per second that the mass would be able to complete is approximately 2.05. Now if I had rounded up to 2.05, then I would say 2.04, which is what the textbook has. Next, a person holds one end of a 30 centimeter piece of string. A mass is attached to the other end. The mass is swung around, so it describes a horizontal circle, uniform rate of 100 revolutions per minute. Angle of we want to calculate the angle of inclination of the string. Okay, now I'm not going to derive the formulas. I'm just going to use them. First, we need to convert our 100 RPM. So 100 RPM is going to equal 100 revolutions, and I want to change that to radians, so 2 pi radians in 1 revolution. And our 1 minute I need to convert to seconds, so that'd be 60 seconds over 1 minute. So you can see how that works with the units. So the revs cancel, the minutes cancel. Go to your calculator, and that is approximately 10.47 radians per second. G is equal to 9.8 for gravity. So cos theta equals G over L omega squared, which is going to be 9.8 over 0.3 times 10.47 squared. Now I'm using the exact value for omega. I'm not going to approximate. So 0.2979. So that means theta has to be approximately inverse cos of 0.2979. And again, I'm using the exact value, and that's 72.67 degrees. So therefore, the angle of inclination of the string is approximately 72.67 degrees. Next, an object is attached to a 1.7 meter long piece of string fixed at point A. The object moves with uniform speed in a horizontal circle. If the tension in the string is 3 times the mass of the object, calculate the angular velocity. Again, I'm going to cheat and just go to the formula. So L is equal to 1.7 meters, and our tension is 3 times our mass, so 3m, where mass equals m. So tension is ml omega squared. So 3m is going to equal m times 1.7 times by omega squared. Those m's will cancel for mass. So we've got 3 over 1.7 has to be omega squared. So omega is going to be the square root of 3 over 1.7, which is approximately 1.33 radians per second. So therefore the angular velocity is approximately 1.33 radians per second.